Okay, guys, welcome back. All right, so now I want to talk about the next topic, and this is going to be uniform circular motion, and this is quite interesting. Okay. So, what defines circular motion? Anybody? Or we should say uniform circular motion. What does this mean? So, what do they mean by circular motion? So, imagine if we're twirling a rope around, like a lasso, right? At the end of the lasso, there's a ball, right? So we're twirling the lasso around, right? Or this ball around on a string, right? When it's saying uniform circular motion, right? What it's implying is that the ball goes around in a circle, it repeats its motion, right? And it has a uniform motion in this direction, right? So what do they mean by uniform motion? Exactly, right? So let's look at the velocity. What's uniform about this motion? So if we're saying that the ball goes around at the same, in the same fashion, no matter where we look at it on the circle, this implies that the speed of it, the ball, is a constant. It's traveling at the same speed, right? It's going around here in a set time. It's repeating that motion, right? Now, let's look at the velocity. Does this mean that the velocity is a constant? Anybody? What does this imply about the velocity?
It's just changing direction, right?
Yes, exactly. Hold on, guys. Hello? Yes, Jesus? I'll keep the 3 o'clock. All right, thank you. So, but the speed remain insane. So how can the velocity change?
Because it's directional. It's vector.
Yes, the direction of it changes, right? And that's really the whole key to this problem, right? Is that the speed remains the same, but the velocity changes. The way you look at the velocity is you look at the tangent at any moment on the circle. So this ball at this instant is traveling in this direction. At this instant, it's traveling in this direction, right? And it's moving along here, right? So if the velocity is changing, what does this tells us about the acceleration? Is there an acceleration? Yes, there is an acceleration, right? Because the velocity is changing, there's an acceleration. But we have to have the velocity change without the speed changing, right? So at this instant, right, there can be no acceleration and along the tangent, right? In this direction, for the speed to remain the same, right, from this point to the next, there has to be no acceleration along the tangent. What this implies is that there's a force that has to be active along the radial direction, or from the center. Let me draw the center actually in the center. So this implies that there has to be an acceleration in this direction, right? And this acceleration is perpendicular to the velocity vector at all points. So you have to realize this. This acceleration vector changes as it rotates around. Well, let me draw. So at this point in time, it's experiencing an acceleration, but the acceleration is perpendicular to the velocity, right? If it's perpendicular to the velocity, it won't change its speed, but it'll give it a y component. I mean, a component in this direction, right? And what will happen is that it will rotate, it will change this velocity vector. And there's a special condition that anywhere along the circle, the acceleration stays pointing inward towards the circle, right? Now, in linear coordinate system, let's say if our coordinate system is like this, where we have x and y, right? The acceleration vector is changing at each one of these positions, right? But if we look at it in a different coordinate system, our acceleration never varies. If we look at it in polar coordinates, 2D polar coordinates, where it's given by, so let's say if we have a point over here, instead of knowing its x and y position, you know, how far do we move up and how far do we move to the right? Instead of that, we have polar coordinates where we see how far out from the center we are and the angle that we have to make. We could use this to define any point that we want, right? Where we have r and theta. And in this case, in our polar coordinate system, the acceleration never changes, right? Because it's always pointed inward along the radial vector, the radius, right? And that never will change, so that we have a constant acceleration towards the inside of the circle. Now, I'm going to skip the derivation for this, but I'll give it to you. So, to keep this circular motion, this uniform circular motion, there's a relationship between the speed of the velocity, the acceleration, and the size of our circle. You can look up on page 119 and 120 for the exact derivation of it, but it's not necessary. So for something to maintain circular motion, let's say a ball on a string, the tension of that ball, of that string, is what's keeping the ball in circular motion, right? The tension provides this acceleration to make it curve, right? And it follows this relationship. So the acceleration caused by the tension has to satisfy this relationship, where it's the square of the speed over the radius. So to have circular motion, we need a radial acceleration inward that's equal to the speed squared over r, right? And in our case, the ball on the string that we're spinning around, the acceleration is provided by the tension force, right? And this acceleration is called the centripetal acceleration. And it's given by this. It's that simple. And then the tension force is called the centripetal force. It's the force that provides this acceleration, right? So whenever you have circular motion, there's always some force that provides this acceleration. So the Earth traveling around the sun, right? We travel in a circular path around the sun. The gravity acts as the centripetal force to provide the centripetal acceleration to keep our path rotating without changing the velocity. And it has to satisfy this relationship. Now, with circular motion, this thing, it's a very interesting phenomena. And what's very interesting about it is that the motion repeats itself over and over again. It's called periodic motion, right? Start from over here and you travel around the circle, and then when it gets back to the beginning, it repeats. And how long it takes to go back to the start is called the period. So the period is how long it takes to do one revolution, right? And in this case, how do we calculate the period? Well, it's the distance it's just the distance divided by the velocity, right? How long does it take to travel around? Well, what is its tangential speed? How fast is it moving around? Is it precessing around the circle? And how far does it travel? So this will be given, in this case, by the speed, by the distance or I should write circumference divided by speed v, right? And in this case, it's 2 pi r, right, divided by its speed, right? So there's a G over here. Okay. Now, there's also something else that we want to talk about. Besides the period, how long it goes around the loop, there's also something called the frequency. Now, instead of measuring the duration it takes to move around the circle, instead we calculate how many times does it move around the circle in a given amount of time, right? So if we're spinning the ball around, if it's moving, if it's making one complete loop in 1 second, that means it has a frequency of 1. It repeats itself 1 time in 1 second. Let's say if the period is 0.5 seconds, so that means that in 1 second it makes 2 full rotations. That means the frequency, or how many times does it occur, is 2, right? The frequency is just literally how many times does it occur in a given amount of time. We usually use seconds. So if it rotates around the circle twice in 1 second, the frequency is 2. And what it ends up coming out to be is that the frequency is equal to 1 over the period, right? If it takes longer to go around, right, we reduce the number of times it goes around in a given amount of, in a given time interval, right? So that means that it's this case. And in terms of number, in terms of symbols, frequency is usually given by F, and it's just 1 over T. Usually you'll either have the period given like this or just a capital T. We'll change that to a capital T. All right. So, and we can rewrite this as the velocity is equal to 2 pi r over capital T, period. Okay. Okay, so why don't we calculate the moon's centripetal acceleration from this, using this, right? So the moon is in circular, uniform circular motion around the Earth. It orbits the Earth, right? Now, this is the moon. It's traveling around. Here's the man on the moon. And let's calculate the centripetal acceleration for centripetal acceleration. So we're given that this distance is is 300,084 kilometers. So yes.
Ну, слушай, если F был зашелкан, он тебя потом перестал.
Andrew, do you have a question or? I'm going to silence. Okay. So it's 384,000 kilometers away. And we know the period. So it takes how many days to travel around the Earth? About 28. It's actually 27.3. And then let's figure out how to calculate the centripetal acceleration. Okay. So we're given this equation. What do we know in this equation? Well, we know R, right? And we don't know A is what we want to find, and then V squared, right? So how can we calculate V squared from the knowns? Anybody? So we'll use that equation I wrote down last time, right? Relating t to the velocity, right? It's just the distance that they travel divided by the speed, right? This gives us how long it takes to go around. A lot, the velocity, right? So then well, we can get v from here. We just transfer v over, right? And now we have the velocity. So let's plug it into this. So then we have 4 pi r squared because of the square root. I'll add the square over here. Right. Over r over t squared. And we end up getting this equation. 4 pi squared times r times divided by t squared, right? And what we find is that the acceleration, when we plug in the numbers, is about 3 to the negative 10th, right? If you compare this with the acceleration due to gravity, it's much, much smaller, about 1,000 smaller, right? Or should we say 10,000 smaller, right? Because acceleration due to gravity is 9.8, about 10. This is to the negative 3. So it's literally no, 10,000 times less, roughly, a little bit less than that. So it actually doesn't. You don't need that much acceleration to keep this in orbit around the Earth, right? And so okay, so I just want to talk about centrifuges real quick. So what centrifuges do is that they separate little particles that are in liquids, usually on the nanoscale or the micro scale. So what you normally have is you have this big device that holds a bunch of test tubes, right? And there's liquid inside the test tube, right? These are the test tubes. What happens is that you have these particles in here, and suspended in the liquid, right? And when we spin this around, right? And as we rotate it around, the particles, the velocity of the particles, right? It wants to continue in this tangential motion, right? Like this. And what provides this, the centripetal force that keeps it in the circular motion is basically the force on the test tube, the force on the water from the test tube, right? The test tube holds the water from in this circular motion, right? That's what stops it from going out at a tangential velocity. And then what keeps the particles in circular motion is the fluid itself. But because the particles can move around in the fluid, the forces, the centripetal force on the particles is never enough to keep it at this radius. So what ends up happening is that the particles move back, and at a time later, once you spin it, they all sediment at this end of the tube, at the end of the tube, because the fluid doesn't provide enough centripetal acceleration to keep it at that distance away, right? It'll start over here, but it'll end up all at the glass, right? And this is what's called the centrifugal force, right? So I'm sure you heard of a centrifugal force, right? And you felt it before, right? If you go around the turn in a car, right, you feel like you're flying outwards from the radius, right? From the turn. So it kind of feels like this. So let's say if we're making a turn, right, and you're in a car, you feel like you're gonna fly out in that direction, right? But that's not the case, right? That's what we call the centrifugal force, right? That's not actually what's happening. What's happening is that we want to fly out in a tangential direction without velocity, right? And it's this component that is what we feel, the component that would be that would make this angle over here. That's what we would feel like as an acceleration in this direction, but it doesn't actually exist. What happens with the centrifugal force is that we feel the car walls pushing in on us, right? And keeping us in this circular motion. And we think that we're actually being pushed out of the car, but it's really the car pushing in on us. So it's that Newton's third law, where we have this reactionary force, right? We're pushing on the car outwards because the car is pushing inwards, and that's what we call the centrifugal force. It's a fictitious force that doesn't actually exist. This doesn't make sense, right? All we have is the centripetal force that's keeping us in this circular motion. But if we have something like a centrifuge, where the centripetal force isn't that great, doesn't exactly cancel out doesn't exactly satisfy this equation, these particles will eventually travel radially outward, right, as they go around. So now let's look at the dynamics of motion with systems like this. So first, let's explicitly calculate it. So for circular motion, as I've said before, we need a force that provides this centripetal acceleration, right? And we'll write this in terms of Newton's second law, right? So the forces, the sum of the forces along this radial direction is equal to MA with the acceleration along this radial direction. Because we have this equation already, right, for circular motion, the radial acceleration has to satisfy this, we can replace it by the speed. So our centripetal force, or the sum of our forces, in the radial direction must always satisfy this to have circular motion. Right? This is the key equation here. Right. And we'll use this to calculate different things. So if we had, let's say if we had a ball, right? Let's say if we had a ball that we were spinning around here, right? Then this force, this tension force, right? If we're spinning this ball around in the air, right? The only force that we have in this radial direction is the tension force. And so we sum up all the forces is equal to the tension, right? And then this is equal to this. And then we can find out how much tension we need to keep it in motion over here before the string breaks. So now let's consider a little bit more complicated problem. So instead of spinning this like a lasso so that the motion is in the circular motion is in the horizontal, what if we rotate it like this? And now the motion is in the vertical direction, right? Let's say we actually spin it like this, right? And we'll have, so now we'll have this, and then we'll have gravity in this direction, right? And let's say we spin it and we want just enough centripetal acceleration, we just want just enough force so that the ball at the very top will continue to move along this arc. So at the very top, we want the ball to continue along this arc, right? Now, so it's operated in circular motion, so let's write down the equations. Let me just write down. So this ball is on a 1.1 meter cord, and its mass is 0.15 kilograms. Right. Right? Min V. So what do we need for this to happen at the top of it? We'll need to just satisfy the circular motion equation, right? Right. So let's write out the equations. So what are the radial forces at this point? There's mg, and then there's also ft, right? So this is mg, over fg plus ft, and then this is equal, this has to equal, satisfy this relationship, right? So we have two forces going that are acting like the centripetal force, right? That contribute to the centripetal force. The tension in the ball, in the cord, and then the gravitational force, right? So here, it has to satisfy this. And the problem X for the minimal V to stay along the circular path, right? We can't change the force due to gravity, but we can minimize the tension force, right? Since gravity is the same direction as the centripetal, the minimal velocity to keep it in circular motion will be when Ft is 0. Right. So that it's just mg that's contributing to the centripetal acceleration here. Right? When we get this equation, we solve, and we find that b is equal to the square root of gr, and this is equal to 3.28 meters per second. So then we solve, and we have our equation. So let's look at this. So it seems like a very easy way to misconstrue this is to say that the fact that the ball is spinning is the centripetal acceleration, right? The centripetal acceleration cancels out gravity, right? That's the wrong way to look at this, right? That whole philosophy of looking at it, we're saying that we have a centripetal acceleration from it going in the circular path, and then this cancels out gravity. That's the same idea as that leads you to this centrifugal force, right? Where you have this force that from circular motion that's pushing out on us. You don't want to look at it like this. The way you want to look at it is that this thing is in circular motion, and for it to stay in circular motion, it needs a centripetal acceleration from somewhere. And in this case, where it gets it from is the force due to gravity, right? So that what you say, instead of saying that the centripetal acceleration balances out gravity, you say that the centripetal acceleration is gravity, right? And it's being used to provide this circular motion, right? This is why we don't, this is why we don't, at this point, fall, while the ball doesn't fall downwards, is because gravity is just being used to move this velocity vector around it, right? Gravity here at this point is the mechanism for the centripetal acceleration, for the circular motion.
Professor, what happened to the FT that's on the right?
This?
Yeah, I went under it.
So,
Yeah.
so we're looking for the minimum velocity to keep it along this circular path, right? And we end up with this general equation right